again. So, so today we will be moving on to the next concept. Last class, when we had discussed about ray optics, that is, in ray optics particularly, we were looking at mirrors. Okay, different types of mirrors, their ray diagrams. That is what I had drawn and I had shown, I have explained. Now we are moving on to the next part. Okay, which is basically the refraction of light. We have looked at reflection. Now we will be looking at refraction. So let me start sharing. I am going to, start up with an animation video so that, you'll be able to visualize things much better. So let's go for a quick, animation and then we will go back, to the blackboard where I will explain stuff again. All right. So let me start sharing the screen and I want you guys to, confirm that you're able to see the shared window as well. All right. So I'm going to do that right now. Okay, so here we go. So I'm sharing a Chrome tab basically. So let me know if you guys are able to see it. I hope the audio is also audible and the video is visible. Okay. So I hope children you're able to see it now. Okay. So let us start.
What happens when light is incident on the surface of a transparent object? Consider a glass slab and suppose the narrow beam of light is incident on one side. The beam of light partially reflects, partially refracts, and is even partially absorbed by the object. In the past, we have already discussed laws of reflection. Do you remember those laws? The first one says that the light ray which is incident is reflected in such a way that the angle of incidence and the angle of reflection are equal. And the second one says that the incident ray, the reflected ray, and the normal all lie in the same plane. Just like for reflection, there are some laws for refraction. And what is refraction? Refraction is the change in direction of light as it passes across the boundary separating two media caused by its change in speed. If the refractive medium is optically denser compared to incident medium, then the refracted ray will bend towards the normal. And if it's optically rarer, it will bend away from the normal. Note that the light is incident obliquely on the surface. When the incident light is perpendicular to the surface, it does not change its direction. There are two laws of refraction. Among them, the first one is same as the second law of reflection. Consider light traveling from some medium 1 to another medium 2, which is optically denser than medium 1. So its speed in medium 2 decreases and it bends towards the normal. The first law of refraction says that the incident ray, refracted ray, and the normal at the point of incidence all lie in the same plane. It means that if I were to draw this on a piece of paper, they all will be on the plane of paper and not out of the paper. What about the second law? The second law is also called Snell's law of refraction. Snell's law gives us the relation between the incident and refraction angles and the refractive indices of the mediums. What is the refractive index of a medium? It is the extent to which the refractive medium increases or decreases the speed of light. Mathematically, it is the ratio of the speed of light in the incident medium to the speed of light in the refractive medium. It's denoted by n and the two numbers in the base are the two mediums. We read this as refractive index of medium 2 with respect to the incident medium 1. Also, V1 and V2 are speeds of light in medium 1 and 2 respectively. We can also define it as the extent to which light changes its direction in the refractive medium. Okay, let's discuss the Snell's law of refraction now. In simple words, it tells us that the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to the refractive index of the second medium with respect to the first medium. Now look at the term on the right. It is constant for light of a given color and for the given pair of media. This is the basic idea of Snell's law, and there are different ways in which we can understand it. In the previous video, we'd seen what n/1 means. It is equal to the ratio of speed of light in the incident medium to the speed of light in the refractive medium. So we can also say that sine I over sine R is V1 over V2. There's yet another way to understand this. We may want to understand the ratio in terms of the absolute refractive indices of the medium. Absolute refractive index, if you remember, is the refractive index of a medium with respect to vacuum. For instance, if the refractive medium is water, then it's written like this. So can we find this ratio in terms of N1 and N2? Yes, we can. We just use some very basic math. We can write this ratio like this, where c is the speed of light in vacuum. Yes, if you simplify this ratio, we will get V1 over V2. And can you guess what the numerator and the denominator are equal to? That's right. This is nothing but the absolute refractive index of medium 2, and this is the absolute refractive index of medium 1. That was another way of understanding the Snell's law. We can also say that sin I over sin R is N2 over N1, where N2 and N1 are the absolute refractive indices of media 2 and 1 respectively. Hope you understood this well. Let's move on to a new page. So these were the two laws of refraction of light. In the next lesson, we will solve a simple example based on Snell's law.
So basically, in this particular animation, we learned what is refraction. So refraction, what does refraction literally mean, right? So when light ray is traveling from one medium to another, the light ray bends or it changes its path, and we call that phenomenon as refraction. So reflection is bouncing of light within the same medium, wherein refraction is the bending of light from one medium to the other. So that is the basic idea. So that is what we looked at in this animation, and they have also discussed what is relative refractive index, what is absolute refractive index. So we'll again go back and look at these concepts in the conventional way. So let me share it. So I'm sharing the blackboard. Yes, let me know if you are able to see it now. So here we are, right? So this is the blackboard that I'm using for explaining. So starting off with today's concept, that is refraction. Okay. So refraction, what do we mean by refraction? Once again, let's have a quick recap. So it is the bending of light as it passes from one medium to another. Okay, so let me write it down. It's the bending of light rays as it passes from one medium to another. Okay, we call that as refraction. So you want to diagrammatically show it. So it's pretty simple. You take a horizontal line. Let us say you have air interface on the top, it's air, and at the bottom you have glass. Okay, it is glass medium. So when I say air, we call air as less denser medium, or we use the term as rarer medium. Okay, when I say rarer, that means with respect to light, the medium allows light to pass in much easily than glass. Okay, no doubt light passes through glass also, but the speed is getting affected. All right, so that's what we need to understand. So in comparison to air, glass would become denser. So we call glass as denser medium and air as rarer medium. So these are the terms that we would typically use. So now let me draw a light ray. So I take a light ray, and the light ray is now incident, say at a point on the air glass interface. Okay, so let me notate this point as O. So at this point, what I'm doing is I'm going to draw a line that is perpendicular. I hope you guys know what it is. It is called the normal. Okay, so the normal makes an angle of 90 degrees to the interface. or the surface where the light ray is typically striking. So it makes an angle of 90. Now, what happens to this light ray as it is incident at the air glass interface? The light ray is going to pass through glass. Now it is traveling from one medium to another medium. The first medium is air. It is traveling from air into glass. Therefore, the light ray is going to bend. Now, how does it bend? It is going to bend towards the normal and it is going to travel on the other side. So you showed the bending of light ray here. Okay. So it is bending like this and it typically travels. Is it clear? So we need to understand. So when light ray enters from rarer to denser, as it travels from rarer medium to denser medium, it would bend towards the normal. Okay, so this is something that you'll have to keep in mind. Wherein if it is the other way around, vice versa, that is denser to rarer, what would happen? How does it bend? It is going to bend this time the other way around, that is away from the normal. Okay, if it passes from denser to rarer. Okay, so the light ray bends away from the normal. So this is how it typically behaves in refraction. So let me mark the points. So light AO is called, the ray AO is called as incidence ray. All these aspects you people know it. Yeah, I've already discussed it in the last lecture. So AO is basically your incident ray, and ray OB we call this is not reflected. Here I will use a different term. We call it as refracted ray. Okay, because it is bending and it is passing through the other medium, right? It is a refracted ray. And what about the angle made by the incident ray and the normal? What do we call it? We call it as the angle of incidence. Similarly, the angle made by the refracted ray and the normal, we call it as the angle of refraction. Okay, so we have both the angle of incidence and the angle of refraction here. So this is the angle of incidence, and angle R is the angle of refraction. Okay, it's the angle of refraction. So these are the different terminologies that you will have to know as far as refraction of light is concerned. Okay. So now we move on. We trying to understand what is Snell's law of refraction. So we have already looked at in the animation video. It gives the relation between the angle of incidence and the angle of refraction, which tells you sine I upon sine R is equal to n, where n is your refractive index. N stands for refractive index. Okay. What do you mean by refractive index? So refractive index is basically a physical quantity that gives you the optical density of any medium. I repeat, refractive index is a quantity that gives you the optical density of any medium. That means the number of refractive index, the value of refractive index will tell you how fast light ray can travel in any medium. For example, it is found that air has got a refractive index of 1.008 something. Okay. But when you say diamond has got a refractive index of 2.42. Can you see the difference? The value has increased, which means diamond becomes denser with respect to air. So air is our reference. So all the refractive index, of different values, or I mean of different materials, are always compared with respect to air. So when I talk about refractive index of water, that is different. It might be 1.3. But compared to air, it is obviously greater. So we say water is denser and rare and air as rarer. Okay, so these are the terms that we would typically use. Okay, so here you have the Snell's law. Let us just mark this. Okay, Snell's law relation is very important. And then we have the relation between the speed of light in air, which is called as c, refractive index n, okay, and the speed of light in a medium v. So we are trying to relate all these three terms, where c is speed of light in air or vacuum, whose value is 3 to 10 power 8 meters per second, and n is refractive index of the medium, and v is speed of light in the medium. Okay, so we try to relate these three terms. What is the relation? The relation goes like this. It gives you that n is equal to c upon v. Okay, this is the relation. So the ratio of speed of light in air to the speed of light in any medium is basically the refractive index of the medium. So we can relate like this using this particular relationship. All right. So this is very useful for us when you solve questions. So we have different, formulas based on this too. So we look at that. We can also say sine I upon sine R from Snell's law is equal to n, which is also equal to c upon v. So these are all the relationships which combines the formulas together. Okay, so this is a combined formula, which is again useful. So with that we proceed. So we have learned Snell's law of refraction, I mean the formula aspect of it, which is important, and we have also related refractive index with speed of light in air or vacuum with the speed of light in a given medium. Now let's look at a simple question for practice. Calculate the speed of light, okay, in crown glass having your refractive index n is equal to 1.5. I repeat, you should calculate what is the speed of light in crown glass having a refractive index of 1.5. So children, what do we do here? Can you tell me, identify the data given in the question? They have given you the refractive index, right? So can you calculate what is the speed of light in crown glass? So what would be your answer? You use the formula.
2 into 10 to the power 8 meter per second.
Yes. So V is equal to C upon N, which gives you 3 times 10 power 8 upon 1.5, which is 15 upon 10. Okay, gets reciprocal. So 2, 3, 3 5s are 15, 5 ones are 5 twos are. Okay, so you get the answer as 2 into 10 power 8 meters per second. That's correct. Somebody gave me the answer. That's right. So the speed of light in crown glass is 2 times 10 power 8 meters per second. So is the speed increasing or is it decreasing as it enters glass from air? Right? Is it increasing or decreasing? By just looking at the value, you can compare. Look at this. What was the speed of light? Yes, 3 times 10 power 8. Yeah, correct. It has decreased, right? It has reduced than what it was before. Now, questions they can also ask you what is the percentage by which it is decreased? So, what will be the answer, children? If the question is what is the percentage decrease in refractive index in N? So, who can tell me the answer for percentage decrease? Yes. It is decreased by how much percent?
33%.
Yeah, 33.3%, right? So 33.33, I think you will get recurring, right? So 33.33%. So it is decreased by a percentage of 33.33. All right. So children, this is how you approach this question. Okay. So yeah. So now let's move on. So we are done with refraction. Now we try to understand what is relative refractive index. Now, relative refractive index is the refractive index of one medium with respect to the other. Say I write it as N12. Okay, this is refractive index of medium one with respect to with this is refractive index of medium one. The light ray is passing from medium one to medium two. The way I have written it, be very careful. Okay, so here when I write N12, you need to understand that light ray is traveling from medium one towards medium two. But when I expand this, the formula becomes N2 upon N1. Anybody knows why? Why do I write N2 upon N1 and not N1 upon N2? I hope you paid attention to the animation, the representation for this. This is because the observer's point of view, we try to understand what is the speed of light in medium 2 with respect to medium 1. That is the reason we are writing N2 upon N1, even though light travels from 1 to 2. Okay, so it is medium 2 with respect to medium 1. So when I read this quantity, I read it as relative refractive index of medium 2 with respect to medium 1, and hence I write it as N2 upon N1 and not the other way around. Okay, so I substitute the formula for this. Now, what is F, the formula for N? It is C upon V, right? So for N2, don't you think it will be C upon V2? The whole divided by, for N1, it is C upon V1. C gets cancelled. So what you get post reciprocally? Once you reciprocal it, you will be getting, will you get V2 upon V1 or V1 upon V2? When you reciprocal, just simplify.
V1 upon V2, sir.
Correct. You get V1 upon V2. Okay. So that's the value that you get. So N12 is equal to N2 upon N1, which is V1 upon V2. Similarly, N21 is going to be equal to N1 upon N2, which is V2 upon V1. So like this, you can relate the refractive indices of different media as light travels from one of them to the other. Okay, this relationship is important for us as far as problem solving is concerned. So we make use of this particular relationship as well. All right. So now we are done with relative refractive index. So now if you multiply all the relative, all the values, okay, say if I multiply N12 times N21, what is my answer?
1, sir.
Exactly. So if you multiply the relative refractive index of the medias, two medias, both of them, one with respect to two and two with respect to one, it is always unity. Okay. So this relation is also useful for certain questions as you solve. All right. So we have looked at different relationships for relative refractive index. Okay. Now when I say absolute refractive index, it is just N is equal to C upon V. Okay. So you just compare it with the speed of light and the speed of light in air or vacuum with the speed of light in a particular medium. So you call that as absolute refractive index. Okay. So this is absolute refractive index relationship. That's it. Okay. So with this, we are done with the different concepts of refraction, Snell's law, and so on and so forth. Okay. So with that, we will move ahead and try to express, go to a higher concept now. Now, what are the quantities on which the refractive index of a medium can depend on? Okay, so we'll see what are the factors that affect the refractive index. Okay, so factors affecting refractive index. So there are different factors that can typically affect the refractive index. So let's see the factors one by one. Okay, the first one is the material of the medium. So material of the medium is very important. So the refractive index is, depends on the material of the medium. If it's diamond, it's different. If it is air, if it's water, if it's kerosene, alcohol, glycerine, paraffin. So different materials have different, refractive indices, and it is definitely, going to affect the refractive indices of that particular. I mean, the of that particular medium that you're talking about. Okay, so this is one factor which depends, which is going to affect the refractive index. The first one is material. Second one is also the color of light that you're passing through it. Okay, so the color of light. So different colors are different wavelengths. As the band of seven colors. As you pass white light through a prism, you know that dispersion of white light would typically take place, right? And you get a band of colors called Vidgaya. Violet, indigo, blue, green, yellow, orange, and red. Okay, it's from bottom to top. That's how it is present. So wherein red is going to have the least frequency but highest wavelength, wherein violet on the other way around would have highest frequency but the least wavelength. Okay, so it depends on the color of light as well. So color of light is also one more criteria based on which refractive index would depend. So refractive index of violet, the violet color would be greater than the refractive index of red color. Okay, it is totally dependent because it is based on the frequency and wavelength as well. So based on that, we can represent. So therefore, when you try to write down the relationships for different colors, so how the refractive index or the indices would look like. So refractive index of violet is typically greater than refractive index of indigo, and so on and so forth. Greater than refractive index of blue and green. Okay, and then you have yellow, orange, and red. Okay, this is the order of refractive index for different colors of light. So based on that, this is how you can place them. Okay, the order how you can place them. Fine. Now you also have a relationship. Third one, it is also wavelength. So depending on the wavelength also you can express. So let us look at that. Now I'm giving you a relation between refractive index and wavelength lambda. Okay, so you need to understand that refractive index is inversely proportional to the square of wavelength. I repeat, refractive index is inversely proportional to the square of wavelength. So when I remove the proportionality sign, you all know you introduce the proportionality constant. So I can write mu is equal to k upon lambda square. So that is the relationship where k is a constant. Okay, so proportionality constant. So this is the relation. So I hope the second concept is clear. So now moving on, second factor is clear. Moving on to the third one. The third factor that can affect it is temperature and density. So temperature and density are also two factors which can typically affect the refractive index of a given medium. Okay. So for temperature, how it is related, I'll tell you. Refractive index is again inversely proportional to the temperature. Okay. So this is how it is related. Now, as far as density is concerned, we say that for density, I'll write the relation here. This one is for temperature. Okay, this is related with respect to temperature. For density, I'll write it on the other side. Okay, so for density, we can say mu minus 1 upon rho. Rho is a symbol that we use for density. Is always equal to constant. Okay, so mu minus 1 upon density is equal to constant. So this is a relationship where the constant can be, k. Okay, so typically when you try to express it, we express it like this. This is for density. So again, the relation is necessary here with terms of density. So we express it like this. Okay, so with that, let's move on. So these are the relationships. Now we'll move on to the next, relationship, which is
Sir,
yeah.
sir, is that constant have any value, sir?
Constant is just a factor. There is no any particular value. Okay, just
Okay,
a
sir.
particular. It's just a factor. That's it. Unitless. Okay, yeah. And
Yes, sir.
fourth criteria that is going to affect density is the surrounding medium. surrounding media can also affect the refractive index. This is also something to be noted. Okay, with respect to what medium it is, the light ray is traveling. So yes, surrounding media also plays a important role. So here comes the concept of relative refractive index, wherein we call it M mu 12 or mu 21 or N12 or N121. Okay, so anyways, it's fine. So we can write it as mu 2 upon mu 1. Okay, so that's the expression. That's the reason, when you multiply the relative refractive index of both the medias as light ray travels, from one medium with respect to the other in both directions, you will get the value as unity, okay, which already I have explained. So these are the different factors that affect the refractive index of any particular medium. So with that, we move on. So again, the formulas, you have to keep it in mind. So moving on to the next important aspect, which is apparent depth. Okay. Now, apparent depth. What is meant by apparent depth? The concept of apparent depth. Okay. Now, apparent means that it seems to be. Okay. So visually, as you see, and when you try to understand the reality, it is different. So apparent means it's basically when object is placed at a surface, below water, you just put it in water. Now, there is something called as apparent depth with respect to the objects present in water. It means it's the perception of our human eye, the way we look at it. So we feel that the object is not that deep; it is quite near to the surface. But once you try to put your arm and you try to grab the object, you would see that your arm would travel much deeper than you expect. So that is because the real depth is different and the apparent depth is totally different with respect to any object. Okay, so that's necessary. So here, apparent depth is basically the depth as perceived by the human eye due to the refraction of light that is taking place from the object from the denser medium to the rarer medium, that is air. Okay, so here there is a relation, children. Refractive index mu is related as real depth. Okay, so let me just write it down. So it is the ratio of real depth upon apparent depth. This is the formula that relates refractive index, real and apparent depth. Okay, so when an object is present, say in a medium that is having density mu, then you try to perceive, the object as with respect to the eye, with respect to the observer, and that perception you call it as apparent depth, but actual depth is different. Okay, actual depth is real depth is something where the object is present exactly the exact measurement. So that is your actual depth with respect to the surface of water, not the perception of the human. All right. So what happens there? Why is there an apparent depth? That is due to something called as lateral shift. Okay. So what is that lateral shift? Let's try to see. Let's try to understand that. So when you have an interface of two media, say this is air, and say this is water. Okay. Say this is water. Say you have an object below the surface of water. Okay. Say we have a coin at this point, at point X. But when a person is observing from here, okay, this is the eye of the person. So when the person is observing, so the person will observe the coin not at X, but at X dash. Okay, that is what is the observing is the person as he observes it. Now, what happens as the person observes? Light from this object is going to travel. Now it travels. You know that the light ray is traveling from denser medium to rarer medium. So what do? You're going to draw a normal there, and the light ray is going to travel away, right? So the light ray will travel away from the normal. So say it will travel away from the normal like this. Okay, so it travels away. But the light ray coming, say from the actual object, apparent position as perceived by the eye is different from the actual object also perceived by the eye is totally different. So here, say again I'm connecting this light ray, so it comes here. So again it is going to typically bend and it is going to reach the observer's eye. Okay, so it reaches the observer's eye. So both of them. I'm drawing it. Yeah, so I should have drawn here because I've taken the output the other way around. Okay, so let us erase this. Yeah, fine. So as perceived by the human eye, now you can see that the real and actual depth is pretty different. So what is real depth and what is actual depth? This depth is basically your apparent depth, okay, and this depth from the surface of water is real depth. Okay, as perceived by the eye, it can come from two different positions. So the human tendency is basically we catch the object which is closer. Okay, so I mean, as perceived by us, so we capture it which is very closer. So that's the reason as light ray comes from the coin, so the actually apparent position of the object tends to be much closer to us than the real position of the object, and that's why there is a difference between actual and apparent position of the object as perceived by the human eye. Okay. So here we need to only understand the relationship between refractive index, real and apparent depth for solving our questions. So this is very, very useful for us. Next, we have something called as lateral shift. Okay. So let's look at that. So we have lateral shift due to a slab. So what is the lateral shift due to a glass slab? So you have a glass slab. Say the glass slab is having a particular thickness T. So T is the thickness of the slab. T is thickness of glass slab, wherein okay, the angle of incidence we can take it as I, the angle of refraction you can take it as R. Okay, so incidence and R is nothing but the angle of refraction. So now let's draw the diagram and try to understand what's happening in lateral shift. So when you take a glass slab like this, okay, and we are trying to show the light ray. Okay, say light ray is traveling and it touches the surface here. At that point, we all know we are going to draw a normal at that point. So we draw a normal. You know that this angle made by the incidence ray and the normal is nothing but your angle of incidence. So this your light ray is traveling from rarer medium to denser medium. So I hope you know what is going to happen. It is going to bend. And how is it going to bend? It's going to bend towards the normal. So it bends towards the normal and it travels. Okay, let me use the same color. So it bends towards the normal and it travels like this. Okay, so once it is traveled there, again we are going to show the normal at that particular point as well. So at this point also we show the normal. Okay, we show the normal at this point. Now, what happens here? The ray, after it has touched the other surface, again it is going to go from denser medium back to rarer medium, isn't it? It goes from denser back to rarer. So when you do that, it is again going to go in the same particular way in which it came. It travels in the same direction as it was incidence in the glass slab. To the direction I am showing it. So you mark the angles here. So what is the angle of refraction? These are the angles of refraction here and here, because that is the refracted ray, and this is your emergent ray. Okay, so this is the angle of emergence. Okay, so we can call it as E, angle E. Now, what we do to find out the lateral shift, we are going to find out the emergent ray. We are going to trace it in the reverse direction. Okay, so by tracing it in the reverse direction, like this, okay, when you trace it, the lateral shift is nothing but the distance between your incidence ray and the reverse the reversal of your emergent rate in the opposite direction. This shift, you call it as lateral shift. What you see here is lateral shift. Okay, so this is your lateral shift. So this is how you identify the lateral shift in the first place. So suppose you have the thickness of the slab as T and the refractive index of the slab is mu. Okay, and thickness, the slab would obviously have some thickness. Okay, so the thickness is T. In that case, you represent the lateral shift. Okay, lateral shift, let me assign a variable for this. Let me call it D. Okay, so we'll write down the formula. So that is D is equal to T upon cos R, where R is nothing but the refractive index. I mean the angle of refraction, sorry, times sine I minus R. Okay, so this is the relation, children. So lateral shift is T times sine I minus R. I repeat, upon cos R, where R is angle of refraction, I is angle of incidence. Okay, so these are the relationships that we use to find out what is these are the parameters which are there to identify, to evaluate what is lateral shift, which is given by D is equal to T sine I minus R upon cos R. Okay, so again, this formula is also important for us as far as numericals are concerned. So we have questions based on this as well. Okay, so this is all about lateral shift. After lateral shift, we have another concept called as total internal reflection. Okay, now what is total internal reflection? What does this term literally mean? Okay, so when light ray is trying to travel from one medium to another, very particularly from denser to rarer, it gets reflected back in the denser medium. I repeat, when light ray travels from denser medium to rarer medium, okay, you know that at this point the light ray is going to bend, right? It bends away from the normal and then it goes. So that is clear to you guys. When you draw the normal like this, it is going to bend away from the normal. Again, you change the angle, it will bend some more, some more. At one point, it is going to be over the interface, and then over a particular time, okay, at an instant, it is going to get reflected within the same medium. So this phenomenon of the light ray getting internally reflected within the same medium as it tries to pass from denser to rarer medium, we call that phenomenon as total internal reflection. Okay, the phenomenon by which the light ray gets reflected within the same medium. Okay, at a particular angle only this would happen. There is a criteria for total internal reflection to take place. That is called as critical angle. Okay, the angle at which, the angle of incidence for which the angle of refraction is going to be exactly 90 degrees. Okay, so you call that particular angle as critical angle. Okay, so that is given by IC. Critical angle we will express using IC. Okay, the light ray is traveling from one medium to another, so we can apply Snell's law. So by Snell's law, okay, the refractive index of this denser medium, you take it as mu. So you can easily represent it. So how do we represent this? You know that by Snell's law, sine I. So I'm writing it as sine IC because it is the critical angle. So sine angle IC upon sine of angle of refraction is R, which is 90. Sine IC upon sine 90 is equal to, you write it as the relative refractive index because light ray is traveling this time from denser to rarer, right? So in denser medium and rarer. So it is moving from denser to the rarer medium. So I can write it as n to 1. All right. So I write it as sine IC. You all know that sine 90 is equal to 1. So upon 1 is equal to, this n to 1 is written as n1 upon n2. Okay. So we can write it as n1 upon n2. So we can write sine angle IC is equal to, now you try to substitute the values. N1 is nothing but your rarer medium, so it is going to be air. Okay, so it is 1. The refractive index of N1 is 1, and N2 is nothing but, say, let's generalize and take it as N. Okay, so any refractive index, it can work for any media. So therefore, what is the value of IC? So IC is sine inverse of 1 upon N. So this is the expression for critical angle. So this is how you get the expression for critical angle. We have derived the relationship. So concept of total internal reflection. And by using that, how you can find out the expression for critical angle. So you can find it using Snell's law. Okay. So this is how you apply it and you do it. Okay. So these are the different concepts, children, which is necessary. Then after this, we have again there are some more for us to cover. Okay, and after that, we can solve the questions. There are different varieties of questions which can be asked, based on this. Okay, so we'll finish off. So many aspects are there. Okay, so I have to go ahead. So we'll move on to the next one. I hope you guys are making note of the formulas, as I'm explaining. So now we are moving on to the next part, which is refraction. Refraction at a curved surface. Curved surface. I mean to say curved spherical surface. Curved in the sense it is spherical. Okay. So what happens when reflection of light takes place at a curved spherical surface? So you take a surface, okay, and let us try to understand how to write the expressions for the reflection. Okay. Now let me take the surface of light on a curved spherical surface. Let me take first a concave surface, a concave spherical surface. Now this is a concave spherical surface. Okay, so we have a concave spherical surface. So now to this interface of the concave spherical surface, this side is going to be the medium whose refractive index is say N2, and this side it is air. So this is typically the spherical surface is having some refractive index N2. So for the spherical surface alone, I'm saying, okay, here it is N2. And it is the other surface on the right hand side is N1. Okay. So, and the radius, this is the radius of the spherical surface. Let us take it as R. Okay. So that is the radius. So you can also draw the principal axis. You can extend it, very similar to your lens concept. So if you're going to have an object here, the object, the light rays from the object is going to go and it is going to hit the spherical surface. From there, it is going to get reflected. Now, you know that it is going to travel from denser to rarer medium. It is going to bend away from the normal. And finally, there is an image that is going to be formed. So object and image. Okay, basic rough diagram we have drawn. So based on this, okay, we are going to write down what is the relationship. There is a formula that we can build based on this particular concept. Okay, as light rays traveling from one medium, that is N2 towards N1, between the interface of a concave spherical surface. Okay, so how do you write down the expression is what we are going to see. Okay, so we have before that we have to mention certain parameters. The distance between the spherical surface, the interface of your spherical surface to your object is object distance. We represent using U. The distance between the surface to your image is image distance, which is given by V. So this is U and that is V. Okay. So we have written that. And now we go ahead in writing the relation. Okay. Now, you know that light ray is traveling from medium N2 to medium N1. Always you will first write down your destination. This is your destination. Destination is where it is going finally, and N2 is your source. Okay, this is a shortcut way of writing. This tip is very useful. Okay, so whenever light ray is traveling from N2 to N1, where N2 is your source and N1 is the destination, you will write down the relation as first write down the refractive index of the destination, which is N1. So N1 divided by the distance between the concave spherical surface to the image that is being formed there, which is going to be N1 upon B. Okay, you will subtract it with from the source from which it came. The source refractive index is N2, right? So that is N2 divided by what is the distance between the interface? It is given by U. The distance is U is equal to, then we will subtract the refractive indices of the destination with respect to the source. Okay, it is going from N2 to N1. So you know what is the relative refractive index. So you will write N1 minus N2 divided by R. So this is the relationship for the refraction at a curved surface. So whenever light ray is traveling from one surface to another, okay, with a curved interface, you will use this relationship and you will find out. Okay, this formula comes very handy for us, when we solve questions. So on the spot, you can write down this formula. You need not derive, which takes a lot of time. So you can write it based on the understanding of the diagram or the figure. Okay, so this is a figure-based approach that we have done. All right. So now we are moving in, to the next part. So let's try to, look at the formulas. So now we have lens maker's formula. So lens maker's formula. So based on the refractive index of the material of the lens, if it is mu, if mu is the refractive index of the material of the lens, so I'm writing it down. Index of the lens, okay, if that is mu, and say R1 is nothing but the radius of curvature. If R1 is the radius of curvature and of the surface that is facing the object, okay, we put it that way, radius of curvature of surface facing object, that is R1, wherein R2 is the other surface. Okay, it's the other surface. Then you can relate using focal length as 1 upon f is equal to mu minus 1 times 1 upon R1 minus 1 upon R2. So this formula we call it as lens maker's formula, where f is your focal length, mu is the refractive index of the material that you're talking about. Okay, material of the lens, very important. And then R1 and R2 are nothing but the radius of curvatures of both the sides. Okay, both the surfaces of the lens. So these are the aspects. Now, if you see, when you draw the lens, I hope you guys would be knowing, we have two different types of lens, convex lens, concave lens. Okay, so convex lens, we draw it like this. So this center is called your optic center. And then you draw the principal axis. Okay. Now here, there are two spherical surfaces. One surface is this, which is R1. You understand? So that is R1. So therefore, this is basically called to F1. And then you have F1, optical center. Then you have F2. And then you have 2F2. Okay. So we need to understand that we know that R is equal to 2F. So what is R1? R1 would be 2F1. Same way, R2 is 2F2. Okay, I hope you get the logic. So the way you express for the convex lens, you easily understand what are the different aspects of the convex lens, be it twice the focal length, which forms the radius of curvature, And the focus, there you can see that there are two focus values that are shown, F1 and F2. We call it as foci. Plural form of focus is called foci. So there are a pair of foci that you can see here. Okay, so this is all about the lens maker's formula. Okay, and I've shown you the lens also. Okay, the two different radius of curvatures are also quite visible. So this is all about it. Okay, and the lens formula is 1 upon, I hope you'll be knowing what is lens formula. Just alter the mirror's formula with a negative sign, you will get the lens formula. Okay, the lens formula is 1 upon f is equal to 1 upon b minus 1 upon u. So this is your lens formula. All right. So like this, you have different aspects, children, to this. So you'll have to be very careful. Okay. So now we have looked at the different concepts so far. Okay. And we'll look at the other concepts also, because if I give you a load you with a lot of information, things might be overflowing. So we have looked at many concepts today. So please go through the material. Okay, I'll share it in the group. Okay. Meanwhile, let's also see the questions. Okay, the different questions from the examination point of view. All right, because this chapter is quite vast, so that's the reason it is quite time consuming. So once we are done with the concepts, all the concepts, we can start with the different numericals also. The numerical aspect also we can begin. All right. So that's it for today. Any doubts you have also you can ask me. Yes, Shalin. I hope you guys have made note of it. Okay, wherever it is necessary. Okay, and then you can practice it. So all the formulas have to be in the fingertips. So this will be shared in the group. Yeah. Okay, so we'll wind up. So I suppose then there are no doubts. So whatever it is, you can even ask it in the chat box. Okay. So feel free, don't hesitate. We are all here to help you. Okay. In case wherever you are stuck, we'll definitely help you out. So then shall we wind up? I think we are done. Okay. So please stop sharing. Okay. Thank you, children. Let's meet up again. Okay. Coming
Thank you, sir.
Friday, let's have another session. Okay. Fine. Bye bye. Take care.
Thank you, sir.
Yeah. Yeah. Welcome.